Data representation and storage in a computer is fascinating. In the last video, we looked at the decimal and binary number systems. In this video, we look at three more popular data representations. I'm Tim Bachowka from the Learn Programming Academy, and this is my Learn to Code series right here on YouTube. Are you enjoying the series? Leave a comment on this video and let me know if you're enjoying it. Alright, on with the show. Data representation and storage in a computer is indeed fascinating. The three popular data representations we're going to talk about in this video are hexadecimal, ASCII, and Unicode. Are you ready? Let's get started. We've already learned that people manipulate numbers using the decimal number system, and computers manipulate numbers using the binary number system. In addition to those number systems, a few more data representation schemes come to mind: hexadecimal, ASCII, and Unicode. Keep in mind the computer still stores all data using binary. Let's look at each of these schemes and see their role in data representation and storage. The hexadecimal number system, often shortened to HEX, is a base 16 number system made up of 16 symbols. As you know, the decimal number system, or base 10, uses 10 symbols 0 through 9. Hexadecimal uses the 10 decimal numbers and 6 extra symbols. In HEX, there are no numerical symbols that represent values greater than 9, so the letters taken from the English alphabet are used, specifically A, B, C, D, E, and F. Hexadecimal A equals decimal 10, B equals decimal 11, C equals decimal 12, D equals decimal 13, E equals decimal 14, and hexadecimal F equals decimal 15. Humans mostly use the decimal system. This is probably because humans have 10 fingers, 10 digits. Computers, however, only have on and off, called a binary digit, or bit for short. A binary number is just a string of zeros and ones, 110111011 for example. For convenience, engineers working with computers tend to group bits together. In earlier days, such as the 1960s, they would group 3 bits at a time, much like large decimal numbers are grouped in threes, like the number 123,456,789. 3 bits, each being on or off, can represent the 8 decimal numbers from 0 to 7. 000 equals 0, 001 equals 1, 010 equals 2, 011 equals 3, 100 equals 4, 101 equals 5, 110 equals 6, and 111 equals 7. This system is called the octal number system and will not cover it in this video. Remember, we're talking about how the computer represents and stores data in binary, but can transform it into decimal for human display and consumption. Moving on, as computers got bigger, it was more convenient to group bits by 4 instead of 3. This doubles the numbers that the symbol would represent. It could have 16 values instead of 8. Hex equals 6 and decimal equals 10, so it's called hexadecimal. 4 bits is called a nibble. A nibble is 1 hexadecimal digit and is written using a symbol 0 to 9 or A to F. 2 nibbles are a byte, 8 bits. Most computer operations use the byte or a multiple of the byte, 16 bits, 24, 32, 64, etc. Hexadecimal makes it easier to write large binary numbers, although hex is still not as easy as decimal for humans. For example, binary 00100100 equals decimal 36 or hex 24. So how did I get hex 24? Well, taking the first 4 bits or nibble, 0010, we convert it into 0 times 8 plus 0 times 4 plus 1 times 2 plus 0 times 1 equals 2, and the last 4 bits or nibble, 0100, we convert it into 0 times 8 plus 1 times 4 plus 0 times 2 plus 0 times 1 equals 4. As I mentioned, to software engineers, hex 24 appears to be simpler to visualize in binary 00100100. Let's try one more. Now this is handy stuff, so don't get too hung up on it. Binary 0011 1110 1000 equals decimal 1000 or hex 3E8. So how did I get hex 3E8? Well, again, taking the first 4 bits or nibble, 0011, we convert it as follows: 0 times 8 plus 0 times 4 plus 1 times 2 plus 1 times 1 equals 3. The next 4 bits or nibble, 1110, we convert into 1 times 8 plus 1 times 4 plus 1 times 2 plus 0 times 1 equals 14 decimal, which is alpha E in hex, and the last 4 bits or nibble, 1000, we convert into 1 times 8 plus 0 times 4 plus 0 times 2 plus 0 times 1 equals 8. Now, as I mentioned to software engineers, hex 3E8 appears to be simpler to visualize than binary 0011 1110 1000. To finish our discussion of hex, the main reason for becoming somewhat familiar with it is because it's much easier to express binary number representations in hex than it is in any other base number system. As I said before, computers do not actually work in hex, but consider that a byte is 8 bits. If we divide the 8 bits into 2 nibbles, 4 bits, the binary value range for a nibble is 0000 to 1111, which is decimal 0 to 15 or 16 possible values. So hence the use of hexadecimal, which can represent the 16 possible values. Now you hopefully have a basic understanding how a computer stores numbers using binary and how binary is translated into hexadecimal. Up to now, we've only been talking about numeric data. But what about other types of text? For starters, how would a computer store alphabetic and special characters like a comma, period, exclamation point, left or right parentheses, etc.? They're not numbers, right? Does the system use another system for storing this type of information? Well, it turns out that the computer uses binary for this type of data also. In fact, for any type of data, it uses binary. Right, so how do alphabetical and special characters get saved in binary? If we're using alphabetic characters, special characters and numbers from a keyboard, the computer uses a table of codes to represent these characters. A very common system exists called ASCII, which stands for American Standard Code for Information Interchange. The first version of ASCII came out in 1963 and it's still in use today. Basically, ASCII is an 8-bit encoding scheme where a unique value is given to each alphanumeric character. In a nutshell, it's a standard way of assigning a value to these alphanumeric characters. As an example, the ASCII codes for the 3 letters that make up my name Tim, all in uppercase, are 84, 73, 77. So T is an 84 or 01010100 in binary. I is 73 or 01001001 in binary, and M is 77 or 01001101 in binary. So depending on how the computer views these binary numbers, they can be considered as the number 84 or the letter T, 73 or the letter I, or 77 or the letter M. Because ASCII is a worldwide standard used on many computers, that means that these codes will be the same and treated the same on all computers all over the world. ASCII was originally based on the English alphabet, A to Z in upper and lower case, and a range of other special characters like the digits 0 through 9, exclamation marks, commas, parentheses, and so on. ASCII uses only 7 of the available 8 bits to represent a character. By using 7 bits, we can have a maximum of 128 distinct combinations, which means that we can represent 128 characters maximum. Now this is pretty limiting for non-English languages, and modern computers have ways to go far beyond this range using Unicode and encoding schemes like UTF-8, UTF-16, and UTF-32. The UTF here stands for Uniform Transformation Form. The point is, though, that with an encoding scheme, there is a value assigned and universally agreed upon for a given value. Where T in ASCII was binary 01010100, in UTF-32, its value is actually multiple bytes. So you've got 00000000, 00000000, 00000000, 01010100. So the computer uses 4 bytes to store each character in UTF-32 versus 1 byte in ASCII. Now don't worry too much about it. The point is that the computer is assigning a specific value to a specific alphanumeric character so that a T on one computer will still be a T on another computer. So this type of encoding works for other types of data as well. Ultimately, the data is still stored in binary. Right, so let's consider one more type of data as I close out this video, an image or picture. So in the example of an image, which is much more complicated than the 3 letters of my first name, it's still a similar principle. An image, for example, a high-resolution picture of yourself, consists of lots of pixels, millions depending on the size of the image. And if you zoom in on the picture, you can see the individual pixels. So your picture has millions of pixels. A pixel needs to store information about the color of individual pixels and the amount of storage space it requires depending on the number of colors. So 8-bit color is where 1 byte 8 bits, can be used to allow the computer to assign a value of 256 colours in 1 byte. We know that a byte can store a number between 0 and 255, so therefore we have 256 possible colour values. In that case, the computer would use 1 full byte per pixel for every pixel in the image. Today's computers use 24 or 32-bit colour, which is why higher resolution images take up much more space. They have more ranges of colours per pixel. Now, I've dramatically simplified things here, but the main point I want to make with binary is that a computer can store virtually any type of data in binary. It's the job of the app or program to use the data in the correct way. Alright, so that's the basics of HEX and Unicode. Drop me a comment in the video and let me know how you found it and whether you've now got a better understanding of HEX, Unicode and ASCII in general. Moving on, in the next video, I'll look at integers, real numbers, alphabetic characters and special characters in more detail. Thanks for watching. See you in the next video. Alrighty, this is the part of the video where I'm meant to get all enthusiastic and to ask you, or quite literally beg you, to subscribe to my channel and to like the video, leave a comment and all that stuff. Well, I'm going to leave that decision in your capable hands to decide whether I've earned a like or a subscribe or a comment. I'd be grateful if you do one, both or all three. My videos will get out there and in front of a bigger audience if I get that level of engagement, but obviously it's your choice. Alright, so remember that this series was meant to be watched in order, so if you haven't watched from the start, then how dare you watch my video series out of order? Click the link over here to get to the first video in the series and watch that if you want to see the entire series in order. Or come over here and click to view the previous video in the series. Again, your choice. Alright, I'm done. Catch you in the next video.